Hello and welcome to this short lecture on surface topography. It is given in two parts, and we will discuss the definition, measurement and characterization of surface topography and surface roughness. My name is Roland Larsson. I'm professor of machine elements at Luleå University of Technology in Sweden. The outline is like this. We'll discuss why study topography. We will discuss the origin, where it comes from, how to measure it, how to quantify it or characterize it, and we will take a look on some examples of engineering surfaces and the topography of them. And you may also read Anton van Beek's book and on chapter 5.1 in this case. So, why study surface topography? That's of course that if you take a closer look on any surface, these surfaces are not perfectly even, they are not perfectly smooth. There is always some irregularities of the surface. There are some few exceptions from that. You may find small spots which are more or less atomically smooth, but these are very rare and they are not used for, normally not used for engineering purposes. So before we continue, I think you should think a little bit. Since we are discussing surface topography in a tribology context, I want you to think about this. What is the best surface topography, or the best roughness from a tribology point of view? And if it is possible to make a perfectly smooth surface, is that the best one? Discuss it with your friend, or just stop the film clip and think about it for a while. Okay, now you have been thinking about it, and I can start discussing it from different perspectives. Some of you are aware of the lubrication regimes and the Stribeck curve, and surface roughness plays of course a very important role in that, in determining which regime a certain lubricated contact is operating. We normally use a definition of the Stribeck curve by using a film parameter, the film thickness divided by some measure of the surface roughness height. And if we say that this ratio, the film thickness, the lubricant film thickness, is much higher, much bigger than the height of the surface roughness, then we are in the hydrodynamic full film lubrication regime. While we normally set the limit of 3, and while it's below 1, we call that boundary lubrication. This is not at all an exact science, but these are good numbers to start with, at least. But of course, in this case, we need to measure, we need to quantify the surface roughness height. When we talk about tribology, we can directly say that there is an optimum roughness, probably, normally. Surfaces mustn't at all be too rough. That is very often a bad thing, because especially if you have two surfaces, one is harder than the other one, and the hard one is very rough, there is a risk that the hard surface penetrates the softer one, and that leads to abrasive wear and high friction. If both surfaces are very smooth, on the other hand, very large real area of contact occurs, and when these surfaces are sliding, high temperatures may occur, and you may have a big problem with adhesive wear and high friction. So in this case, there is probably an optimum roughness and also an optimum hardness combination. Okay, but why study and measure roughness then? Well, We have been discussing the tribological applications, of course, since the roughness controls how much the asperities penetrate the other surface. They also influence the surface stress and then also the wear risk. And as we discuss, it influences the lubrication regime, and it also influences the friction and the wear. There is also other reasons to measure and study surface roughness. Is, for example, if you are working with surface finishing methods, you really need to define how smooth the surface is and how smooth it needs to be, and you have to be able to communicate it in different levels in different engineers in a company, for example. Should this the machine designer should tell the people in the factory how to make the surface, how the surface should look like. So it's not only the height of the roughness, it's also the appearance of the surface. And another area where surface roughness plays an important role is electric conductivity. If you have an electric switch, for example, you really need a good conductivity to make it possible for the current to pass through the switch. And it's the same in heat conduction. If you really want good heat conduction, or bad on the other hand, surface roughness also plays an important role. Some problems in surface roughness is that it's pretty difficult to understand how this roughness influences tribology and how it influences wear and friction. There is no really definition about that. So it's not only the roughness that plays a role here. It's a combination of many different factors, where surface roughness is one of them. And so this lambda value, the film parameter, as we discussed in the Stribeck curve, is far from sufficient to say if a lubricated contact will have high friction or high or low wear, for example. There are cases where lambda below 1 can give you full film lubrication and no problem at all. And sometimes we also see that surface roughness doesn't really play a very important role in friction, for example. If you take two steel surfaces with different surface roughness within a reasonable span of surface roughness heights, then you may find that the friction is more or less the same. It doesn't really matter if the RA is 0.3 micrometers or if it's maybe 2 micrometers. And then it's also that if you measure a new surface, that's one thing, but after, when you have been using it in a tribological contact for a while, it will be run in and it will be worn, slightly worn, and the highest peaks will be worn down, and actually normally the surface becomes smoother. And even if you start at 2 or 0.3 micrometers, you may run into the more or less the same roughness in the end. So it's pretty tricky to understand how exactly roughness influences tribology. Okay, where do these surface irregularities come from then? Well, first of all, they come from what kind of production process you use, a surface finishing process you use. It's different if you use turning or grinding or you polish the surface, or if you coat the surface with something. All these surface finishing processes will create different surface roughness height, but also different appearance of the surface. The material structure also plays a role, of course. If you have a very brittle material, that will create more sharp corners, sharp asperities, while you have a more ductile material, it will be probably smoother. And that is and of course in the end it is controlled by the atomic structure of the material. And as I also discussed earlier, that how you use the surface will also influence how the surface roughness looks like. So if you wear it, if you run it in, if there is some chemical action on the surface like corrosion or some tribofilm formed on the surface, that will also change the surface roughness, surface topography. It's also important to define what is surface roughness. Is it if we measure the surface roughness of a cylinder, for example, we can't, if surface roughness height of a cylindrical surface, we must distinguish between the form and the waviness and the roughness. The form is of course the cylindrical shape of the surface, while the roughness is the small irregularities on top of that cylindrical shape. So and there are no clear limits where the form starts and the roughness begins, and intermediate waviness, what that is there is no clear definition for that, but roughness is of course the very short wavelengths. Then we talk about a micrometer scale, while form is more the millimeter scale normally. So this is also a matter of how you measure and what you are going to use the surface roughness or surface topography measurement for. That is maybe the most important thing here. You must think about, why do I measure surface roughness? What do I need it for? Then you can distinguish between form and roughness and useful roughness. But of course you must think about the size of the tribological contact you are going to use this surface in. If the contact is 1 millimeter, then it's reasonable to measure over that distance too. The different types of measurement then, well, the most classical and still very often in use is the Stylus instruments. You are using a kind of needle or stylus which you are moving along the profile like this, and this needle or this stylus is moving up and down, and you have a transducer that records how this stylus is moving. And then you can scan a surface, and you can scan it in, that gives you a 2D graph of the surface, but you can also move it back again and take a new trace just near the previous one, and you can scan a number of traces like this. That gives you a 3D description of the surface. But nowadays we are more and more using optical methods to directly measure a three-dimensional landscape of the surface roughness. Then interferometry is used. And we should also think about that there are another type of Stylus instrument which is called scanning probe microscopy. It's more or less the same as the Stylus instruments, but in a much smaller scale. In this case you are scanning millimeters, while in this case you are scanning micrometers. So, and depends on what you are going to use it for. If you want to learn about the very fine details, this is the instrument you are going to use. If you want a more engineering approach, you want to learn maybe the surface roughness over square millimeters, then you're going to use one of these two instruments. And you should also remember that surface topography measurements are never exact. As I understand, or as we have seen also, that is, even if you measure the same spot 2 times, you will get different answers. And if you use the same technique at different laboratories, you will also get an even bigger difference, even if you measure the same surface. This is just a picture of one of the older instruments here, of Waiko, and this is an example of how such a measurement look like afterwards. So you get a 3D landscape of the surface, and in this case you can see that there is some wear track here, or something has happened here. One important thing is that when we represent or when we visualize surface roughness, we normally looks like this. It looks like very sharp asperities, very sharp roughness here. And so earlier we used to say that putting two surfaces in contact is like putting Switzerland into contact with Austria. But this is not really true because you normally plot this at different scales. So you magnify the scale in the y direction much more than in the x direction. So if you use the same scaling in both directions, the surface looks like this. This is a more normal appearance of the surface roughness. So maybe we should say that putting two surfaces together is like putting Sweden in contact with Finland, or Belgium in contact with the Netherlands instead. So, and that is because the asperity slopes are rarely steeper than 10 degrees, so maybe more often closer to 1 degree, because especially after they have been used for a while, they have been run in, then you cut off the very sharp asperities. As I have already indicated, there are big problems in measuring the surfaces, and all these instruments I mentioned, they have their own problems. The Stylus instrument have a problem that the tip radius is maybe too big. Even if it's a pretty sharp tip, it can't come down in the deepest valleys, and it might even damage the surface because it's in contact with the surface. So if the tip is harder than the surface, it may scratch the surface. The optical methods are better because there is no contact then, but on the other hand, the equipment is much more expensive, and there are also things that can disturb the optical measurement technique, for example transparent films on the surface. Scanning probe microscopy is much more sensitive and much more accurate, and also can give you much more details. On the other hand, it's can be even more expensive, and it's also very sensitive. You need the operator must be trained pretty much before it can be used, and also the very small measurement spot creates problems, because you may misinterpret the surface roughness if you just measure a very tiny spot by 1 micrometer. And here are some examples from a company Indexator in northern Sweden. They were early in adopting that optical measurement technique, and this is a surface measured by them. It's a turned surface, and it's also a little bit worn, I believe. And this is another machine surface, and this one is also slightly worn. And this is an example of how you can use then the tool to study the surface, and you can see the difference here. If you measure the 3D pattern, and then you make a 2D graph of the in the y direction across the grinding or the turning marks, or along the lay of what we normally call the lay of the surface roughness. This is along it, and this is across it. You can see here, clearly see that how the wavelengths, typical wavelengths in this surface. So that ends part 1 of this lecture, and in the next part we will discuss how to characterize this surface topography. Can we find a number of parameters that describes the roughness in a reasonably good way or not. Thank you very much.